Did NASA's James Webb Space Telescope observe a planet in a distant solar system that might support life? In a groundbreaking moment for astronomy, the James Webb Space Telescope has pierced the vastness of space to capture an image beyond our solar system. This isn't just any image. It's a revelation that could reshape our understanding of the universe. Today, in this video, we will discuss the recent image captured by the James Webb Telescope that could uncover secrets about habitable planets. In 1963, Russian astrophysicist Nikolai Kardashev introduced a groundbreaking concept to measure the developmental progress of civilizations based on their energy consumption, known as the Kardashev scale. Developed while studying the quasar CTA 102 and contemplating the potential existence of extraterrestrial civilizations far more advanced than humanity, the scale categorizes civilizations into three types. Type 1 civilizations can harness the entire energy of their planet, Type 2 can utilize the full power of their host star, and Type 3 can tap into the energy of an entire galaxy. Do you know where Earth stands on this scale? Let us know your thoughts in the comments section below. The Dyson sphere, proposed by physicist Freeman Dyson, is a theoretical structure for capturing a star's total energy to detect advanced alien civilizations. Variants include the Dyson swarm, a collection of orbiting solar collectors, and the Dyson shell, a massive star-enclosing structure often featured in sci-fi. These constructs would shift a star's radiation towards infrared wavelengths, aligning with energy conservation laws. In 2016, NASA's Curiosity rover made an unexpected discovery when it found trimite in a rock sample from Mars' Gale crater, challenging previous beliefs about Martian volcanism. Researchers later explained that the mineral likely formed in an underground magma chamber before being ejected during an eruption. This discovery has significant implications for understanding Mars' geological history. The 2018 discovery of organic molecules on Mars by the Curiosity rover sparked intense interest in the search for Martian life. Fluctuating methane levels on the planet have led to theories ranging from comet impacts to possible microbial activity, while meteorites like the Nola meteorite offer intriguing clues with their complex carbonaceous materials. However, the question of life on Mars remains unresolved. The InSight mission, which landed on Mars in November 2018, has been studying the planet's geological structure with a heat probe and seismometer. It recently recorded its strongest quake yet, with a magnitude of 5, puzzling experts about its origins. On February 18, 2021, NASA's Mars 2020 mission landed the Perseverance rover and Ingenuity helicopter on Mars to explore the possibility of past microbial life and prepare for future human missions. Perseverance will analyze rocks for biosignatures and study the planet's climate and geology, while also converting CO2 into oxygen. NASA's James Webb Space Telescope recently identified an exoplanet, K2-18b, located beyond our solar system, which shows potential to sustain life. The telescope detected methane and carbon dioxide on this planet, which is about 8.6 times larger than Earth. These findings suggest that K2-18b might be classified as a heme exoplanet. Exoplanets refer to planets located outside our solar system, and the term heme is derived from merging hydrogen and ocean. It characterizes planets believed to possess hydrogen-dominant atmospheres coupled with oceans of liquid water, as explained by Space.com. Additionally, dimethyl sulfide, DMS, is potentially present on K2-18b. On Earth, DMS is a compound typically associated with living organisms. According to NASA, K2-18b is positioned within the habitable zone, implying its proximity to its star could permit the presence of water on its surface. Such regions are often termed Goldilocks zones, inspired by the classic children's tale, signifying that the conditions are ideally suited for life. The planet exhibited high levels of methane and carbon dioxide, with a noticeable absence of ammonia. This suggests the possibility of an ocean beneath K2-18b's atmosphere, rich in hydrogen. As per NASA's observations, the presence of DMS on the planet has led scientists to speculate about the possibility of life there. This is because, on Earth, DMS is produced by phytoplankton, a type of marine algae that serves as a food source for marine life and is synthesized through sunlight. Niku Madhusudan, an esteemed astronomer from the University of Cambridge and the primary author of the study, stated that future observations from Webb should determine if significant amounts of DMS truly exist in K2-18b's atmosphere. K2-18b, positioned within the habitable zone, is known to contain carbon-based molecules. However, this doesn't automatically imply it can sustain life. Given its substantial size, about 2.6 times Earth's radius, it's believed that the planet might possess a vast mantle of high-pressure ice, similar to Neptune. Yet, it might have a thinner hydrogen-rich atmosphere and a surface ocean. While high-pressure worlds are theorized to feature vast water oceans, there's also a possibility that K2-18b's ocean might be too hot to support life or remain in a liquid state. Subhajit Sara from Cardiff University elaborated that, while our solar system doesn't have a planet of this kind, subneptunes are the galaxy's most prevalent planet type. Their detailed spectrum of a habitable zone subneptune has allowed us to identify its atmospheric molecules. Characterizing exoplanets' atmospheres, which involves determining their gases and conditions, is a burgeoning field in astronomy. However, the brilliance of their much larger host stars often overshadows these planets, making studying their atmospheres challenging. To overcome this, the team analyzed the light from K2-18 star as it traversed the planet's atmosphere. Being a transiting exoplanet, K2-18b causes a diminution in brightness as it moves across its star's face. This method led to its initial discovery in 2015 via NASA's K2 mission. During such transits, a minuscule portion of the starlight travels through the exoplanet's atmosphere before reaching instruments like the James Webb Space Telescope. This journey of starlight through the atmosphere leaves identifiable marks, enabling astronomers to deduce the atmospheric gases of the exoplanet. The remarkable sensitivity and extended wavelength range of the Webb telescope made it possible to detect spectral features with just a couple of transits, robustly highlighted by Sudan. To put it in perspective, a single transit observation with Webb offers precision similar to 8 Hubble observations taken over several years and within a more limited wavelength spectrum. Savas Constantino from the University of Cambridge added that our current results, based on just 2 observations of K2-18b, are merely the tip of the iceberg. They showcase the potential of Webb in studying exoplanets within the habitable zone. Their findings have been approved for publication in the astrophysical journal Letters. The research team is gearing up for further studies using Webb's MIRI mid-infrared instrument spectrograph. They anticipate that this will validate their current results and shed light on the conditions prevailing on K2-18b. Sudan concluded with a broader vision. Our endgame is to identify life on a habitable exoplanet, reshaping our understanding of our position in the cosmos. Our current insights mark a significant stride toward comprehending heme planets in this grand journey. While planets such as K2-18b remain largely enigmatic, according to NASA, some space researchers are optimistic about their potential as sites to uncover life. Sudan emphasized that their research highlights the need to explore a variety of potentially habitable settings when looking for life beyond our planet. While traditionally the quest for extraterrestrial life has been centered on smaller terrestrial planets, the expansive heme planets present a more favorable environment for atmospheric studies. As our ongoing voyage through the cosmos continues, the James Webb Space Telescope emerges as a symbol of humanity's ingenuity, revealing the universe's hidden secrets. Will the James Webb Space Telescope be able to find civilization beyond our solar system? As our understanding of the universe expands, the discovery of potentially habitable exoplanets becomes increasingly significant. The James Webb Space Telescope, JWST, is at the forefront of this exploration, offering unprecedented capabilities to study distant planets. The telescope's ability to analyze exoplanet atmospheres and detect specific gases is revolutionizing how scientists approach the search for life beyond Earth. By studying the chemical composition of these atmospheres, researchers can infer conditions that may be suitable for life, helping to refine the criteria for habitable planets. One of the most remarkable aspects of the James Webb Space Telescope is its ability to observe exoplanets in the infrared spectrum. Infrared light allows astronomers to peer through thick clouds of gas and dust that often obscure visible light observations. This capability has proven essential in studying distant worlds like K2-18b, where the telescope has already provided crucial data. Webb's sensitivity to infrared radiation enables the detection of spectral features that indicate the presence of molecules like methane, carbon dioxide, and dimethyl sulfide, DMS, all of which could signal biological processes. These molecules are considered potential biosignatures, which are compounds that could be produced by living organisms. The discovery of DMS on K2-18b is especially intriguing. On Earth, DMS is primarily produced by marine phytoplankton, which play a key role in Earth's ecosystems. The presence of such a compound on K2-18b raises the possibility that life could exist there, or at least that the planet has conditions that could support life. While the detection of DMS is not definitive proof of life, it does suggest that K2-18b might have an environment that could foster biological activity. Scientists are hopeful that future observations will help clarify whether the presence of DMS on K2-18b is a sign of life or simply a byproduct of other processes. In addition to atmospheric analysis, the JWST's ability to study the physical characteristics of exoplanets is also enhancing our understanding of these distant worlds. For instance, the telescope can measure the size, temperature, and surface conditions of exoplanets. By studying the size and mass of a planet, astronomers can estimate its density and composition. This is important because the presence of liquid water, a key ingredient for life as we know it, depends on a planet's temperature and atmospheric pressure. Planets like K2-18b, located in the habitable zone of their star, may have the right conditions for liquid water to exist on their surface. However, not all planets in the habitable zone are suitable for life. The size of a planet plays a crucial role in determining its habitability. For example, K2-18b is much larger than Earth, and its size suggests that it may have a thick atmosphere and high pressure, which could make it inhospitable for life. It is also possible that K2-18b has an ocean of water beneath its atmosphere, but this ocean may be too hot to support life, or it could be in a gaseous state due to high temperatures. Despite these uncertainties, the fact that the planet lies within the habitable zone of its star and shows signs of having an atmosphere rich in key molecules makes it a promising candidate for further study. The discovery of planets like K2-18b is part of a broader effort to identify potentially habitable exoplanets. Astronomers are using a variety of methods to detect exoplanets and analyze their properties. The most common method is the transit method, which involves observing the dimming of a star's light as a planet passes in front of it. This technique allows scientists to determine the size and orbital characteristics of the planet. Other methods, such as radial velocity and direct imaging, are also used to study exoplanets, but the transit method has proven to be the most successful for identifying planets in the habitable zone. While the search for habitable exoplanets is still in its early stages, the potential for discovering life beyond Earth is becoming more realistic. The discovery of exoplanets with Earth-like conditions could provide valuable insights into the origins of life in the universe. For example, studying the atmospheres of these planets could help scientists understand how life might arise on other worlds. By identifying planets with similar atmospheric compositions and environmental conditions to Earth, astronomers could gain a better understanding of the factors that make a planet suitable for life. The James Webb Space Telescope's contributions to this field are just beginning, and future missions are likely to build on its findings. As the telescope continues to observe distant exoplanets, scientists hope to uncover even more evidence of habitable worlds. The ability to detect and study exoplanet atmospheres in such detail is a game-changer for the field of astrobiology. With each new discovery, the possibility of finding life beyond Earth moves closer to reality. In addition to its scientific implications, the discovery of potentially habitable exoplanets raises profound philosophical questions. If life is found on another planet, it would challenge our understanding of our place in the universe. The existence of life elsewhere could suggest that life is common in the cosmos, and that Earth is just one of many planets where life has emerged. On the other hand, the lack of life on other planets could imply that life is a rare and precious phenomenon, making our planet even more special. These questions are not just academic. They have the potential to change how we view ourselves and our future. As we continue to explore the cosmos, the search for extraterrestrial life will likely become a central focus of human exploration and scientific inquiry. The James Webb Space Telescope, with its groundbreaking capabilities, is playing a crucial role in this endeavor. As we learn more about exoplanets like K2-18b, we may be one step closer to answering one of humanity's most enduring questions. Are we alone in the universe? The discovery of potentially habitable exoplanets such as K2-18b also underscores the importance of space exploration in the broader context of human survival. While the idea of colonizing other planets is still far from reality, the study of exoplanets and the search for life beyond Earth could inform future efforts to protect and sustain life on our own planet. Understanding the conditions that support life on other worlds may offer insights into how we can address challenges such as climate change, resource depletion, and the sustainability of human civilization. In the coming years, the James Webb Space Telescope will continue to push the boundaries of our knowledge and inspire new generations of scientists and explorers. The discoveries it makes could have profound implications for both science and society, shaping the future of humanity's journey into the cosmos. Whether or not we find life on planets like K2-18b, the search for answers will undoubtedly deepen our understanding of the universe and our place within it.